Hello everyone and welcome to another live stream of Physics 212. That's Physics with Calculus. We're doing electromagnetism. Today we're going to talk a lot about DC circuits with resistors and Kirscoffs rules and other fun things like that. If we have some time, we're going to go into RC circuits as well and kind of talk about the difference between a DC circuit and RC circuit and stuff. To start out with, I want to post a few links in the chat for those who are watching. First, there's our Learning Center's website, which is pdx.edu/learning center/tutoring. Definitely check them out for different tutoring resources and other resources they have available. You can also follow them on Facebook and Instagram. There's links for those there. I also have an attendance sheet. Fill out the Google form there and get some extra credit just by putting in your name and who you are. That way your teacher knows that you showed up to these lectures. Let's get started and start talking about DC circuits. So DC circuits, we talked a little bit about how capacitors work in a circuit before. DC circuits deal with kind of how resistors work in a circuit. So we can have resistors in parallel or in series, and the difference between those is series circuits, as you might know, we have some voltage supply, and they would kind of be lined up in line with each other. So I'm going to draw a few of them here. Let's do one more. And there's a rule on kind of how to find the total resistance in a circuit, in a series, with series resistors at least. We would say that the total resistance, R total, is going to be equal to the sum of all of them. So R1 plus R2 plus R3. Oops. And we kind of saw something similar to that in capacitors, except for capacitors, it was the parallel circuits that we added up the capacitance for it. Here, the series circuit, we add up those resistances for them. And that's for series. If we want to talk about circuits in parallel, or resistors in parallel, we could draw another circuit. This time, I'm going to draw 3 resistors in parallel. That's connected. And here we can say we have R1, R2, and R3. To find out the total resistance in this circuit, we can just, it's the same as capacitors in series, where the reciprocal 1 over R total is going to equal 1 over R1 plus 1 over R2 plus 1 over R3. And I like to write this as R total is equal, put a little bracket there, put that 1 over R1 plus 1 over R2 plus 1 over R3, and just take that whole thing to the -1 power. It's really easy to put into the calculator. You just put these fractions into the calculator, add them up, and then take the answer for that sum and take it to the power of -1, and that gives you the reciprocal of that and gives you the total resistance totally. So now we can apply this, and they ask in this question, what is the largest and smallest resistances you can obtain by connecting a 44 ohm, a 42 ohm, and a 294 ohm resistor together? So based off of these rules for series and parallel, you can see that the maximum resistance we have is going to be when we add these resistances together, because that's going to be the largest number we're going to get. If we were to do this, these numbers are all smaller than the total resistances, and in fact our total resistance here should be smaller than the resistances up here, and we'll see that here in a second. So the largest resistance we can have is to add all of those together. So let's do that. We can say that our total max, I'll say R max. Shoot. R max is going to equal the sum of all of them in series. So that'd be 44 ohms. Let's use omega. Plus 42 ohms plus 294 ohms. We add all those together. Clear. 44 plus 42 plus 294. And that equals 380. So that's 380 ohms. Real simple calculation to make. We're just adding them together, and that's going to be the maximum resistance we have in there. To find out the minimum, we just have to add all those resistors in parallel to each other. So instead of adding in series, we add in parallel. So again, now our minimum is going to equal 1 over 44 ohms plus 1 over 42 ohms plus 1 over 294 ohms. I'm going to take that whole thing to the -1 power, just so we can find the reciprocal of that sum. Doing that, put parentheses, 1 divided by 44, plus, I should probably go way back to the beginning. I'll insert an extra parenthesis. That can take the whole thing to the -1 power. Parenthesis 1 divided by 42. Add to that parenthesis 1 divided by 294. And then take that whole thing to the -1 power. And that will be 20.04 or 02. Where'd it go? 44, 42, and 294. Okay. So it's 20.02. 20.02 ohms. And notice that this is a smaller resistance than any of the individual resistances, because by taking the reciprocal and summing up the inverse of each of these, we get much smaller values. This next problem has to deal with 3 appliances connected in parallel. So here they give us the wattage of a toaster, the wattage of an electric frying pan, and the wattage of a lamp. I'm going to plug all of those into a 15 amp circuit. And when you plug it into your wall, you're basically plugging a device in parallel with everything else in your house, right? So we need to draw a circuit diagram of the toaster, oven, frying pan, and lamp, and label the currents passing through each device. So looking at that, the diagram would kind of have this voltage supply there, which is going to be like 120 volt, 15 amp supply. And that's just what standard comes out of the wall plugs of your house. It's 120 volts. Most circuits are about 15 amps. Some in the kitchen might be 20. And then I'm going to draw this circuit here and go down. I'm just going to put little boxes and say that's a toaster. I'm going to connect in parallel to that. Another little box. This is a frying pan. Just a diagram to show how these devices are connected together. Draw another one. This one's going to be my lamp. And if we were to take a voltmeter to this, so let's say I had just some device that measures my voltage, right? And I connected it here and here. I'd get a certain voltage. I'd get that same voltage if I connected it here and here and here and here, because that's all the same circuit. There's no real resistance drop between there, or no real resistance between there, so there's no voltage drop between those points. Excuse me. So we have the same voltage going to each of those appliances. So we can use that idea that the voltage is constant at 120 volts, okay, to find the current. And this is just applying the idea of what power is, right? Because power is equal to current times voltage, right? So we can do that for each of these devices because we know how much power it is. We can use that to find the current just by dividing each side by voltage. So we can say then the power divided by the voltage is going to equal our current. And that's what we need to find out for each of these. So I'm going to write the power on each of these. So it's 1840 watts. That's 1360 watts. And that's 72 watts. So to find the power for each of these, or the current going through each of these devices, we can take the power individually and divide them by 120 volts. So in this first case with the toaster, I'll say P sub T is going to equal 1840 watts divided by 120 volts, which is going to equal 1840 divided by 120 is 15.33, and this is going to be in amps. We can see that the power of the frying pan is going to equal 1360 watts divided by 120 volts. 1360 divided by 120 is 11.33. And I should note this first value we got here, 15.3 amps, that's already greater than the total amperage the circuit can handle. So we already know there's too much current going through here. So if we can continue on and we can find the power then of the lamp, which is going to be 72 divided by 120. 72 divided by 120 is 0.6 amps. And we can sum all these up. So we can say this plus. Now it's just an experiment to find out how many total amps we're actually drawing. So that's equal to 27.3 amps, which is much more than the 15 amp circuit. So the question is, will the 15 amp breaker blow? The answer is yes, it will. Because this one alone is too powerful for that. That toaster is a pretty powerful toaster. So you definitely can't do that in the frying pan at the same time, because even a 20 amp circuit is going to blow there. So we can move on. In this one, we want to find the equivalent resistance between points A and point B, where R is equal to 5 ohms. And here you see there's 4 resistors. They're connected kind of in parallel and in series at the same time. So I'm going to redraw this so it's a little bit clearer. This is how I like to look at it, at least. There's different ways you can kind of look at this. So I'm going to draw 2 groups, 2 clusters of resistors. And this is point B, this is point A, the other. So really we have 2 resistors in parallel, which are then connected to 2 more resistors in parallel. So I can call this kind of group 1 and this group 2. And each of those are going to be 5 ohms. So what I could do is find the total resistance of group 1, because since they're parallel circuits, I can say our total is equal to 1 over 5 ohms plus 1 over 5 ohms, taking that whole thing to the negative 1 power. Plugging that into our calculator, I can say 1 divided by 5. I always forget my first parenthesis. Plus 1 divided by 5. Close. Taking it to the negative 1 power is equal to 2.5 ohms. And notice it's half the resistance of either one of them combined. So when you have the same resistance on both of them for 2 resistors in parallel, we are going to have half the resistance at the end of it. And that's going to be true for cluster 2 too. So that's also going to equal the same thing because these have the same 5 ohm and 5 ohm resistances. So to add up the total, the absolute total, I probably should have called this one R1 and then R2, which is equal to R2. So then R1 plus R2 is going to equal my total resistance, which is equal to 2.5 ohms times 2. So there's 2 of them. Equal to 5 ohms. So that's kind of the way to do it. Whenever you have any circuit and there's like a bunch of different things connected in different ways, just break it down piece by piece and say these two are in parallel to together. What's the total resistance there? And we can add that on to any other resistors that are in series. And if we have to, we might have to cluster things together, find groups of resistances and add those all together. It's a real systematic way of doing it. But once you get the system and the process down, it's not a super complex thing to do. We're going to talk a little bit about Kirscoffs rules next, which is another fun way to find the current through different loops as they're happening. And there's 2 rules behind Kirscoffs rule. The first is a junction rule, which says the sum of all currents entering a junction must equal the sum of all currents leaving the junction. So how I like to say that is kind of what comes in must go out. So all the current going into a junction must leave the junction as well. So if I say I1 is there, I2, and I3, that means that I1 must equal I2 plus I3. Because the net current going through every junction point should be 0, basically. So if you have a positive going in, you have 2 negatives going out, and you can sum up all of those currents to equal 0. And we'll see an application of that. We're going to go through a couple different circuits. Secondly, there's the loop rule. And this is the algebraic sum of charges in potential around any closed circuit. Charges in closed circuit. So it's basically a loop that we're looking at for these closed circuits, this closed circuit path. So I'll put loop here. Must be 0. So what that means is using the idea of Ohm's law, which is V is equal to IR. If we take any positive voltage supply, any EMF that we have, we can go around any closed loop, and at every resistor we can calculate the voltage drop of that resistor using the current times the resistance. So if we take the total voltage added plus the voltage drops going around any loop, we're always going to equal 0. And that's one of Kirscoff's rules there. So let's try and apply this to a circuit. Here I have this circuit here. You can see there's a couple loops, there's a couple junctions, and they give us some values. What they don't give us is a voltage supply and current values, right? We don't know the value of I2, I3, and V1, but we know the resistor values and everything. We know the value of V2, and we know the value of I1. So using those values, we can create a system of equations basically using Kirscoffs rules to solve what these three values are. And if you remember, you need 3 different equations at least to solve 3 different unknown variables. That's any system of equations. You need the same number of equations as you have unknowns. So I am going to write first with the junction rule. So the junction rule would tell me that the current going in to this junction here, right, that's the junction I want to look at, because I know the current's going into that junction. I know I1 needs to equal, I guess, the current going in. So I1 plus I2 is going to equal I3. You could also write this simply as anything that's going out of it can be a negative current. So that's I1 plus I2 minus I3 is equal to 0. I can write, use purple. So then I can define 2 different loops at least that I need. There's 3 loops in here total that we could use. We could use this loop here, kind of going around in this direction. We can use a green, this loop here, going around that direction. And we can use the full outer loop if we wanted to. Any of those 3 loops is fine to use. We could write equations for all 3 of them. We only need 2 more on top of the junction that we have. So I'm going to pick the 2 smaller loops. Now I'm going to start with V1. So V1 is going to be equal to the voltage drop across R1. So that's going to be, it's V1 minus the voltage drop across there. So that's R1 I1, because that current going through here is I1. And then we're going to go down through here. So that's going to be minus the current drop. But it won't be minus really, because it will be plus, because our current is going in the opposite direction of our loop. So we're going to add. We're going to be gaining voltage in that situation. So that's going to be R2 I2. And then it would come back around to there. So that whole thing should equal 0. And that's 2 equations that we have now. We need 1 more equation. That's going to be our green loop. So the green loop should be starting, I like to start at voltages, so, and go in the direction of the voltage. Find that it helps. So our current going this way, because the same current here is I3, it's also going to be going this way, the same direction as our loop is going. So it'll be a voltage drop. That's R3, I3. And that's going to go up here, same direction as the current. So that's going to be minus R2, I2. And that whole thing should equal 0. So now we can just use these systems of equations to solve for it. We can plug in the values they give us, and we can start doing some substitutions in there to figure out what we want. So first thing I can do is use this junction over to the right and say that I'm going to solve for I2, which is equal to I3 minus 2 amps. Put it in red. So that's just plugging in the value for 2 amps that we have coming from our current up on top. Similarly, I'm going to use, on this purple loop here, I'm going to plug in the values we have for that. That's V1 minus, this is going to be 2 amps times 12 ohms. Kind of wrote it backwards, but the 2 amps is the current from I1, and the 12 ohms is the resistor value. We're going to add to that the resistance of R2, which is 6 ohms, times I2, which we don't know. Let's say that whole thing is equal to 0. We can then plug in the value for I2 that we have over here. So say that V1 multiplying 2 amps times 12 ohms is going to be minus 24 volts because amps times resistance is ohms. V is equal to IR plus 6 ohms times I2. I'm plugging in our value for I2. That's 6 ohms. Is going to be times I3 minus 2 amps. Still equal to 0. I can do a little bit of distribution there. Just to simplify a little bit, it's V1 minus 24 volts plus 6 ohms times I3 minus 12 volts equal to 0. Yes. So adding those up, we get V1 is equal minus 36 volts plus 6 ohms I3 equal to 0. Let's move on to the green equation because we still have 2 unknown variables in that purple one. Plug in the values we know. V2 is 21 volts. I'm going to subtract from that. R3 is 5 ohms. I3 minus R2, which is 6 ohms. I2, we can substitute in I2 from over here. So that's going to be I3 minus 2 amps is equal to 0. Simplifying a little bit, we got 21 volts minus 5 ohms I3 minus, distributing that negative 6 ohms in, I have negative 6 ohm I3 plus 12 volts, which is equal to 0. Adding those voltages together, I get 33 volts. In this case, I only have one variable left in there, so I'm going to move all the terms with I3 to the right side and combine like terms. So that's going to equal 11 ohms times I3. And then we're going to divide by 11 ohms. So that's 33 divided by 11. And we have volts divided by ohms, which is going to give us current in amperage. So that's 3 amps is equal to I3. I can go up, plug that into my junction equation to find I2 is equal to 3 amps minus 2 amps, which is just going to be equal to 1 amp. So I have 2 of the 3 variables I need. Now I just need to plug in for my third. Move down, give me a little bit of space. And we can see then that V1, this should be a 6. I'll move, I'm going to move everything to the other side of the equation. So V1 is going to equal 36 volts plus 6 ohms times current from I3, which is 3 amps, which is equal, I'm not going to equal 0, and I'm going to make this one negative because I'm moving it to the other side of the equation. So that one has to be negative. So then 6 times 3 is going to be 18 volts. So V1 should equal 36 volts minus 18 volts, which is 18 volts. 18 volts. So using Kirscoffs rules, we were able to find the voltages for everything we were looking for. We got V1, we got the current I3, and the current for I2, all there. And that let us satisfy all the different possibilities in that circuit that we had there. Let's go on and try another one. This is a similar type of thing. We have 2 loops and a junction we're going to be looking at. I'm going to use this loop here and this loop over here, make a thicker line. There we go. Might be easier to see. And again, this junction up here, junction B as well. Here, they give us the voltage values, they give us the resistor values, they don't give us any of the currents. So our current values are going to be the key that we're looking for. In this case, I can say I1 is going into that junction, minus I2 minus I3 is equal to 0. Because I2 and I3 are coming out of the junction, so they have to be negative values. Going around our loop, this first loop, A, B, E, F, A, the orange loop, I like to color coordinate. It's a little bit more clear what's going on. And again, I'm going to start with my voltage supply. It's a little easier. So I'm going to start with V1 minus R1 times I1 minus R2 times I2 is going to equal 0. And that's just going around that loop. The voltage drop across here, the voltage drop across here. The current on each of these is in the same direction as my loop, so that's why they're both voltage drops. They're both negative values. And then my third loop, draw a little bit farther down here. Let's see if I can get it all in the same frame. It's going to be, so notice my direction of my loop is going this way, but my voltage supply is the opposite. My positive to negative current is going the wrong way. So I'm going to call this a negative V2 plus, I'm going to add, because again, my loop is going this way, but my current is going downwards, the opposite direction of my loop. So I'm adding R2, I2, and then going this way across here, that's the same direction as my current. So I'm going to subtract R3, I3. And then going down this way, we're still on I3 current. There's not a different branch here, but we have two resistors along there in series. So this is going to be a minus R4, I3. And that's all going to equal 0. Move that equation down now that we've written it. Give us a little bit of space to work. And we can start plugging in some values. So first, let's solve for one of the currents. In this case, I'm going to solve for I1. So I1 is equal to I2 plus I3. And then substituting that into the orange equation, or plus adding the values we know in there, that's going to be 24 volts minus, that's 3 ohms, which is R1. I1 we don't know, so go back to orange. I1 minus R2, which is 3 ohms. I was going to substitute that in, but I did not, which is equal to 0. So I'm going to substitute in for I1 there. I2 plus I3. Just plugging in the value from the blue equation there. And we can do a little bit of distribution, and simplify. So that's going to be 24 volts minus 3 ohms I2 minus 3 ohms I3. Say minus 3 ohms I2 is equal to 0. Just distributing that negative 3 ohms to each of those currents. Notice I can combine two of those I2 terms now. So 24 volts minus 6 ohms I2 minus 3 ohms I3 is equal to 0. So we have two equations there, I2 and I3. We need to move down to the green equation, and we're going to solve for one, either I2 or I3. So let's see, and I think I solved for I2. So, and we're going to plug in first the values that we know. So V2 is 29 volts. So this is 29 volts negative plus R2. R2 is 3 ohms. I2 minus R3, which is also 3 ohms, times I3 minus R4, which is 4 ohms, times I3 is equal to 0. We can combine the I3 terms. There's 2 of them, so it would be negative 7 ohms there. And we're going to move that to one side of the equation. Be negative 29 volts plus 3 ohms I2, and that's going to equal, say, 7 ohms I3. We can actually move this voltage over here and make it positive. That'll be the next step to do, is we're trying to isolate I2 ultimately. So then we just need to divide by this 3 ohms. So when I divide by 3 ohms, I get I2 is equal to 7 over 3. Notice the units ohms are going to cancel out there. Times I3 plus 29 divided by 3. And the volts are no longer going to be volts, because using Ohm's law, V is equal to IR. When I divide V by R, I get current, so this is going to be in amps. So now I have solved I2 in terms of I3. So I can go back and plug this up top here to get a value. So rewriting this, I'm going to move, let's move I3 over to the other side also. 24 volts minus 6 ohms. That's not substituted. Let's change that there, so we can see that I'm substituting in for I2 my 7/3 I3 plus 29 over 3 amps minus the 3 ohms I3, which is equal to 0. Now I can do some distribution there and see what we get. So I need to go back. Colors. Okay. So that's 24 volts minus 6 ohms. Well, I guess let's do that distribution. 6 ohms times 7/3. There's a common factor there of 3, so I can cancel the denominator there and say it's 2 times 7, so that's going to be 14. And then ohms times amps is going to be volts, because V is equal to IR. So this is volts. Oop, this should be, yeah, whatever value of I3 is. And I guess I can just put over or times ohms. So that's going to be a value in volts when we're done, but I can't quite cancel that out yet. Doing the same thing, that negative 6 ohms times the 29 over 3 amps. Distributing that through, we're going to end up with double of that 29. Double of that 29 should be 58, if my math is right, plus 58 amps. Oh, again, amps times ohms is going to be volts in this case. And then we're still going to subtract in that 3 ohms I3 equal to 0. Now we just have I3 to solve for. We can combine a few like terms, the 24 and the 58. Oh, this 58 should be negative, because I didn't distribute my negative through. So 24 minus 58 should be a negative 34 volts. I'm going to move everything else to the other side, so that's going to be a positive 14 plus 3 amps. All right, so 14 plus 3 is 17 ohms, I3. And then we can divide by that 17 ohms, which is one of the last steps we need to do. So negative 34 divided by 17 is just negative 2. This is negative 2. And then volts divided by resistance, or ohms, is going to give us amps, is equal to I3. So there's our current for I3, which is a negative current. Plugging that in down below, we can then say that I2 here is going to be equal to 7/3 times a negative 2 amps plus 29/3 amps. Doing that, we end up with a negative 14/3 amps plus 29/3 amps, which is equal to 15/3 amps, which is, of course, 5 amps. So that's the current for I2. And we have the current for I3, so we can plug those in to find now I1, which is equal to I2, which is 5 amps, and then I3 minus 2 amps, so that's going to equal 3 amps. So using Kirscoffs rules, we're able to find the current for all 3 of those branches of the circuit up there, and we can double check. I mean, we just kind of did here, but all the current going into this junction is equal to the current going out of the junction there. It's also good to note the current on I3 is negative. That negative current there for I3, we assumed, based on the diagram, the current was flowing in this direction. Since that current came out as a negative value, it's not going in that direction. It's actually going in this direction. So anytime you create a loop, if you're not sure what the current is going in and out of different junctions, make your best guess for it. The math will fix you for it. Anytime you come up with a negative current, you have to flip the direction of your current on your diagrams, and just the understanding of, because the current is going to go flow positive to negative all the time. And notice in this case and this case, we can look at those voltages. This has a higher voltage, so it's going to be pushing current here a little bit harder than the current is pushing there. But this also has 2 resistors to work at, so really letting the math work out the values for you is the smartest thing to do. Next, I'm going to do a quick overview of RC circuits, and if we have time, I'm going to run through solving one problem. So RC circuits have a slightly different behavior than DC circuits do. With DC, it's really just, it's a direct current. The current's always going to be the same until you branch off from it, at least. But the current stays constant within each branch. With RC circuits, since we have capacitors in there, those capacitors charge up. And as the capacitor is charging up, the charge on a capacitor will slowly increase, the current going into the capacitor will slowly decrease, and the voltage of that capacitor will slowly increase as well. Flip side is, if you disconnect that capacitor as well, the capacitors will also discharge and basically create a negative current going the opposite direction. And when they do that, the opposite effect is true. So we can define the charge, the current, and the voltage using some exponential equations that are all fairly similar to each other. So first we're going to look at charge. And this is the charge over time. So as the capacitor charges up and it gets those two parallel plates get a greater and greater charge until it's fully filled, is going to equal that EMF, which is the voltage supply times the capacitance, times 1 minus an exponential e to the power of time divided by tau. And tau is your time constant, right? So we call where tau is a time constant. And really it's just equal to the resistance times the capacitance. And that defines how quickly it decharges to a certain percentage. In this case, it'll charge up to about 63% of its full value within one time constant. And we can show that kind of looking at this equation that we have here. As t approaches that value, that time constant, RC, we're looking at the exponential term, or that binomial, 1 minus t to the negative, I'm going to write RC here instead of tau. We can see that behavior. That behavior is going to approach this 0.632. Because as it approaches, I can really say that e to the negative t over RC is equal to e, or approaches e to the negative 1. Because once t and RC are equal value, that fraction becomes just 1, and e to the negative 1 power is just 1 over e. And if you plug that into your calculator, you get like 0.368, which is what the value we have there while it's discharging. Notice I can say this is charging and this is discharging. So that 1 over e value, if we subtract that from 1, we get this 63%. So that's 63% of the total capacitance, the total charge on the capacitor is going to be there after one time constant. And notice after about 4 time constants, the capacitor is basically fully charged on there. Similarly, after 4 time constants, it's about fully discharged. And it's an exponential, so it never really gets fully discharged based on the math, but I'm sure eventually it does get to be a neutral charge. We can also look at as t approaches infinity, as time just goes on and on and on and on, this exponential, e to the negative t over RC, that's going to approach e to the negative infinity, which is basically 0, right? So then we're multiplying by 1 minus 0, so we get this 1 minus 0 term in our equation up here. So as t approaches infinity, our charge Q of t is going to equal just the voltage supply times the capacitance, VC. And that goes back to our definition of a capacitor, where we said capacitance is over to Q over V. Rearrange that a little bit. We can see that that's CV equals Q. So the charge of the capacitor is going to equal the voltage times that capacitance. Looking at the discharging, you can see that as discharging has a slightly different equation involved with it. In this case, we're not doing this 1 minus the exponential. It's really just the initial charge, whatever charge that capacitor has on it, times e to the negative t over RC. So it's very similar, but now we don't have that 1 minus part in the term. And that's equal to Q of t so we can see the behavior of this as t approaches RC. We see that that e to the negative t over RC is going to approach e to the negative 1, which is just equal to 0.368. So that's why here we're just multiplying that 37% or so of the original charge is going to be or we're discharged down to 37% of the original charge at that point. Once we hit one time constant, when the time is equal to the resistor times the capacitance. Similarly, as t approaches infinity, we can see that e to the negative t over rc is going to approach e to the negative infinity. Again, this is equal to 0. Because that's equal to 0, q naught times 0 is equal to 0. And you can see that in the graph here, where as time goes on forever, we basically approach 0. So looking at the graph, understanding how those equations work for them, we can determine the charge on it at any time and kind of see what it is. We can also use math to solve for that time, so see what the charge would be at a certain time, just plugging in values for t, or how long it would take to get to a certain different charge to solve for a value for t. Same idea with current. The equations are a little bit different for current, but it's really a very similar idea where we have an exponential decay and an exponential growth, essentially. Or I guess it's a logarithmic growth. So for charging, this one's going to be charging current and discharging. The equation for these is I of t is equal to the maximum current times e to the negative t over rc. So again, as t approaches rc, as it approaches the time constant tau, we can see the behavior of this acts similar to a discharging of a current, or a discharging of the charge, where e to the negative t over rc is going to approach e to the negative 1, which is about equal to 0.368. So multiplying that by the maximum current that could happen. Notice the maximum current is when there's no charge on the capacitor and it's charging up. So the current's flowing as fast as it can. But as that capacitor charges up, the current gets smaller and smaller and smaller until it goes down to 0. And we can see that in the equation. So as t approaches infinity, e to the negative t over rc is going to approach e to the negative infinity, which is equal to 0. So see, at that point, current is equal to basically 0 after about 5 tau. For the discharging, so it acts logarithmically. Notice it starts out as a negative current. So we have 0 kind of way up here. That's like that due to the fact that once the capacitor is charged, once you disconnect the battery source, the voltage supply to it, it starts to discharge, and electrons flow in the opposite direction they did while they were charging. So we have a negative current on there at that point. So we can say that here that the current is going to equal, say, I naught. That I naught is this initial epsilon, or say EMF over resistance, which is a negative EMF over resistance, times e to the negative t over rc. So again, this is an exponential function. It's going to be a negative exponential function, which is why it's flipped down. And it's got this exponential decay, kind of logarithmic decay up to 0. We can see the behavior of this as time is approaching rc, one time constant. Again, e to the negative t over rc. rc is going to approach e to the negative 1, which is equal to 0.368. And again, as time approaches infinity, this is going to reach t rc approaches e to the negative infinity, which is equal to 0. So it always approaches 0, and eventually we have 0 current going through there. Remember, it starts out as a negative current and kind of decays up to 0. And this is for the current in an RC. Last thing we want to talk about here is the voltage. So the voltage in an RC circuit, again, it works the same. There's an I in there somewhere. the same basic way where we have a charging and a discharging. Here the charging is kind of a logarithmic scale. It goes up to a certain value until it's fully charged. It has the same voltage as your EMF. That's this value here, that EMF, your voltage supply. And when it discharges, it starts off at whatever voltage it was charged up to, and it decays down to 0. So this is discharging. Now we can see the behavior of this based on the equation. I can say the voltage of the capacitor is equal to that EMF times 1 minus epsilon, the exponential to the power of negative time times RC, which is your tau, time constant. And looking at the behavior as t approaches RC, we can see that 1 minus e to the negative t over RC is going to approach that 1 to the negative, or to the 1 minus e to the negative 1, which is equal to 0.632. And that's how we get that kind of logarithmic rise or exponential decay up to that EMF voltage. Just having this 1 minus that exponential decay. So the amount that we're subtracting from that is decaying. As t approaches infinity, these are the two parameters I like to look at, because we're looking at one time constant. We can look at 2 time constants, 3 time constants, and kind of see that pattern, but it's really just going to show us that pattern of it to a certain degree. We can see that 1 minus e to the negative t over RC is going to approach 1 minus e to the negative infinity, which is equal to 1 minus 0, so that's just 1. So this whole term becomes 1, and the voltage on the capacitor ends up being just what the EMF voltage is when it's fully charged. Similarly, when it's discharging, the equation there, it's going to have that exponential decay going down. So it loses that 1 minus, similar to how the charge was. The voltage on the capacitor is going to equal to the original voltage, e to the negative t over RC. So we can say that as t approaches RC, the e to the negative t over RC is going to approach e to the negative 1, which is equal to 0.368. And that's where this value comes in. At 1 time constant, our voltage has discharged down to about 37% of the original voltage on there. As the time approaches infinity, as it goes on forever, we can see mathematically that e to the negative t over RC, our time constant, which is tau, is going to approach e to the negative infinity, which is equal to 0. So once this is equal to 0, we can see the voltage of the capacitor basically is equal to 0 once it's discharged completely, which makes sense. And those are the 3 types of things we look at for RC circuits: the charge on the capacitor, the current that's caused from the capacitor charging or discharging. Notice when it's charging, the current starts off at its maximum and then gets weaker and weaker until the current's very small. When it's discharging, it starts off at kind of the negative of what the maximum current was and then discharges down to 0 current. The voltage starts off at a 0 voltage and then builds up this voltage, which equals the voltage supply. So the voltage across the capacitor, once fully charged, should equal the voltage supply voltage. But once you disconnect that voltage supply, you can see that voltage start to be released. The power starts to be released from the capacitor, and it'll discharge that voltage, and the voltage will decay exponentially. That's all the time we have for today. Again, I'm going to paste the attendance sheet into the chat window. Make sure to fill that out if you haven't already. And you can also schedule an appointment with tutors. There should be a link above my head if you're watching on Pingy to schedule an appointment with a tutor. I also have drop-in hours starting at 2 o'clock, which is going to be right now, and going until 3 o'clock. So stop in if you have any other questions, and have a great day and enjoy the wonderful weather we're having compared to last weekend.